Thank you very much for the invitation and the introduction given by Dr. Zhao. So I'm very happy to get this great opportunity to share some of my past study on solar city. So uh, I proposed the concept called solar city. Uh, I think it has three meanings. First, we model our city as a 3D city or three-dimensional city, not in 2D. Second, we estimate the spatial and temporal distribution of solar irradiance over 3D urban surfaces. And the third, we do the solar farming and utilize the, let's say, green electricity effectively in different ways. So based on my past study, we have three subsections, but maybe I would like to share the first two parts due to the limitation of time. So for the first, solar urban planning, well, currently cities occupy 2% of land on Earth, but consume around 16 to 18% global energy. That accounts for more than 75% of CO2 emission. And that global warming and air pollution and make the urban heat island effect more severe. Even now, we know that we have the Glasgow Climate Change Conference in UK, right? So I think it's imperative for us to use renewable energy alternatively to develop livable cities. And for solar energy, it has been increasingly being used during most recent years. So if we want to use, let's say, do solar farming or in cities, for the first problem we need to solve is the solar estimation, because it's still quite different from the rural areas. It's not like the large solar PV plants in, let's say, in Egypt, in California, in the northwest part of China, that is utility scale that can directly connect to the national grid. But if we do solar farming in cities, in most cases, probably it is the distributed PV system. So we should consider the shading effects from the surrounding buildings. So many models has been proposed, but overall, we still have some problems. First, some models cannot support complex geometries over the buildings, such as the rooftop are concave polygons, or when the rooftops are nested with each other, more complex geometries. And also, when we want to estimate this solar distribution, which means in cities, we need fine spatial resolution. So in this case, the computation load for a large urban area would be extremely large. And also, previous models does not estimate the solar accumulative or dispersive process. And this solar accumulation is very important. So previous models, we consider direct and diffuse radiation. That's good. It works well for rural areas, mainly covered by vegetarian. But in cities, because in some big cities like here in Hong Kong, we have many tall buildings equipped with glass or mirrors that we have very high reflective radiation. So we cannot ignore this. But even for the water family software, ArcGIS, it does not support this functionality. So that's our motivation, okay? For example, here, there is a building that a solar irradiation pass through the atmosphere and arrives this facade or vertical surface. It's like an arc. And it reflects back to the ground to make a solar accumulation process that can melt cars and set buildings on fire. But actually this location, just the right location, good place to equip with PV modules, right? If you look at the right picture, this is exactly in Hong Kong, in Victoria Harbour. You're gonna see a very bright sunshine. That is the reflection from this top building. So we should consider this. When I was a PhD student, we've already estimated the solar distribution on all the rooftops in Hong Kong. At that time, we mainly focused on the cloud probability mapping. The major reason is that Hong Kong is a mountainous area, so it's significantly influenced by cloud cover. So this is the major focus at that time. And then we consider more complicated scenario, as I said, 3D city. So the idea actually is quite simple. We consider multiple reflections, urban morphology, which means the surrounding buildings, the shadow effects from the surrounding building. The third is historical weather, which we might consider the historical cloud cover that determines the transmittivity and diffuse proportion, which further determines the direct and diffuse solar irradiation. For geolocation, this refers to the latitude of the city. So the idea is quite simple that if I use this laser, so if we have a footprints of the building and we have the height attribute, height information enriched with this height attribute, we can create or generate this vertical 3D polygon for all the 4 surfaces together with this rooftop. So which means essentially from this example is 2.5D, right? And then based on location and time, we can determine the solar irradiation as a 3D vector. And these two 3D vectors pass through these verticals of this rooftop, we can generate 3D shadow polygon, right? So this is the most simple case, and we consider concave buildings that is blocked by the other facade of the same building, or the shadow was blocked by the other building. This is just a simple case. In real algorithm or real development, sometimes we have different scenarios that we have to consider. And I'm not going too much details for the algorithm. This is the output. Essentially, here every dataset is in 3D. I just visualized in 2D. Okay, so you see that this 3D shadow line, these blue shadow polygons. So this 3D shadow polygon intersect with the rooftop marked as the blue shadow line versus intersects with the facade marked as this 3D red shadow line. So all the space below these shadow polygons and shadows are in shadow versus other places are in light. It's quite simple, right? So so the next, we estimate the solar irradiation without reflection. That is A for A. Boundary information either in shadow or in sunshine. Here, we represent this by using 3D point clouds, and we generate these 3D point clouds from the 2D building polygon, not from the real measurement by using laser. Okay, so in this case, we can determine the spatial resolution. So, for example, 1 point represent 1 square meter area for easy computation and statistics, and B is the result after the first reflection, and C is the ultimate step after multiple reflections. Okay, this is a typical big data computation. Imagine that in a very small area here in Hong Kong Polytechnic University, the area is much smaller than my campus at KTH. So we can easily generate 7 billion point clouds. The total number is not that much large, but consider that if we consider multiple reflections, which means we could consider the same 7 billion 3D vectors to represent the solar irradiation. One vector will associate dozens of the point clouds. So for one intermediate result, to estimate the solar distribution at one location, one instant of time, we can easily generate several millions of the point clouds. So this is just not just the record in the database, but also the computation as well. So this is a huge challenge. So we built this model purely based on the PostSQL supported by PostGIS. And we want to achieve parallel computation because even though we know that PostSQL has support parallel SQL query, but sometimes the optimization plan is not that much good or satisfied. So we use this Java Eclipse by calling the multiple threads simultaneously. So in this case, we can do parallel computation. This is the general idea. So then we did the field measurement. We measured the solar irradiance from the early of the morning to the late of the afternoon on the ground, on facade, and on rooftop. Then this is the result. In the x-axis, that is albedo, which means the reflection ratio. Okay, so you're going to see that in most cases, with the increase of albedo, the relative error are decreasing. But for the first two sites, for site 1 and site 2, for these two rooftops, it's the same. The reason is that these two rooftops has already at a very high level. There's no other contribution from the reflections because the rooftop is already very high or high enough. So we applied this model in 10 different cities. Totally, we have 16 study areas. What does this mean? So it means in some cities, we have 2 comparative study area. So even in the same city, we can compare the different influence from the urban morphology. You're going to see that, for example, here, this is Los Angeles with a small h means the high, small l means low. So in Los Angeles, we have basically in the downtown area, we have a high density of tall buildings versus we have a residential area, basically we have low density and low buildings for comparison. Okay, so we calculate half the year considering the several multiple effects as I just mentioned. Interestingly, we find that actually New York City is listed at the very top level, even though New York City has already at a very high latitude, right? And Singapore is listed at the second place, and this is reasonable because it's almost on the equator of the Earth. In Hong Kong, we have good location, but it's not that much good compared with many other places. The major reason is that Hong Kong is mountainous, so we have a relatively thick cloud cover compared with other cities in the same latitude. And also we calculated, we call it the solar capacity. This means that we calculate the whole of the solar energy maintained by the area divided by the total solar irradiation or solar energy coming to the same study area. Because we consider multiple reflections, some of the parts are reflect back to the atmosphere. So that's the major reason, okay? And then we did the concentration analysis. Well, if we want to install solar panels in cities, we would like to find a location that we have solar radiance that is quantitatively large and spatially concentrated. I think this is reasonable, right? Quantitatively large, which means we can generate larger amount of electricity by using the same PV module. Spatially concentrated means that we want to find a location that we can install a larger size of PV module instead of just split it into multiple small pieces. That is not good for installation and the inconvenience for maintenance. That's the major reason. So we did this test. Then to answer a scientific question, what is a good city to use solar energy? To answer this question, I developed some incidents to represent urban morphology. And then we use these incidents to make a correlation with the solar capacity we calculated for each urban area. You're going to see that, for example, here we have cosine alpha or other incidents like the density of a solar facing area, the density of brightness areas on building surface, and the average height of the buildings, etc. So in most cases, we have a strong and positive correlation. What does this mean? So this means urban morphology has a strong effect to the solar capacity. But look at figure A. We have cosine latitude, and the correlation, Pearson correlation, capital R, equals minus 0.47. So what does this mean? So this means the location of the city, I mean the latitude, the location of the city will be has some influence to the solar capacity. But this is not a conclusive factor. I think this is a good news for Nordic countries if some Nordic cities want to utilize solar energy, right? So this is a short conclusion. Urban morphology has a strong effect to solar capacity of 3D cities. Singapore is one of the best cities to use solar energy. Effectively utilize solar energy in Hong Kong is a bit challenging. Then this model can be used in different real applications. For example, here, this is the new columnist area. It was not utilized before. Previously, this is the Qide Airport in Hong Kong. Then the government has already established a large initiative to transform this area at the business district and shopping malls. So we build now, currently, we are building cluster of new buildings here, tall buildings. And so we should consider the solar transformation or the changes of solar accessibility for the existing surrounding buildings. Because in residential area, in office, we would like to have abundant solar sunshine, right? And for urban vegetarian, like trees or grass in urban area, we would like to have moderate sunshine. And it's not like in Nordic countries. Here in Asia, people, especially females, when they are walking along the street, they don't like big sunshine. Okay, they do not want to get a sunburned. They want to keep their skin white. So this is a different culture. So for pedestrians, they would like to have less or no sunshine. So this is a very interesting phenomenon. Okay, but anyway, we utilize this model and compare different urban morphology. One is the existing one. The other is the master plan of buildings established by the government. We make a comparison and we find that, okay, wow, this is a good urban planning because in different hours of the day and different seasons, the existing buildings are not that much influenced by the new buildings. Consider that, well, in cities, we may not always use rooftop. Sometimes rooftop area is not that much enough. And it's challenging to utilize ground surface because it is related with the government, right? You may need to get the permission and it's related with the urban planning. So some people, they are utilizing these street noise barriers. This is a real application. It has already been built in the Netherlands, for example. So we use the Baidu Street View images. It's a little bit like Google Street View images, okay? And we detect these noise barriers because it's quite close to this residential area, is too noisy. So we detect this by using deep learning method, and based on the orientation or azimuth and the location, we can estimate the solar PV potential on solar noise barriers, okay? And also in Europe, we have very good quality, high quality of OpenStreetMap data that represent a high accuracy of rooftops. But in many different countries, like in developing countries, this data set sometimes is unavailable. So people are trying to extract these rooftops accurately by using deep learning and to estimate the solar PV potential. This is a case study in Nanjing, in Jiangsu province, China. This is my hometown, okay? Lastly, earlier of this year, I came up with an idea that maybe we can estimate this, extract this PV module, large solar PV plants, and to investigate the environmental impacts. So we did the preliminary study by using Google Street View images, and also we utilized the PlanetScope, this 3 meters spatial resolution. Okay, but and then we also extracted these PV modules from the rooftop. But now, just roughly 2 weeks ago, there's a publication that they have already done quite similar work. And this is a really good study. It has been published in Nature. So if you are interested, you can read this. This not belongs to us, okay? So I make this solid line to divide it down. And the second part is about solar charging over shared scooters. So during the past few years, it has raised more than 7.7 billion US dollars for micromobility, like bike sharing or scooter sharing. So it's a huge market, even though in the most 2 years, because the disruption of COVID-19 and sometimes and some places it is influenced significantly. But I'm still optimistic for this service. So we utilize the historical data, and this is the real data from the two companies, scooter sharing operation. One is from Grab, the other is from Neuron in Singapore. This is one study area in NUS, National University of Singapore. This is basically in the downtown area of Singapore. So it is split. This operation is not done in whole the city, just at the restricted small areas, because previously it was a dockless sharing service, which means you can borrow and return scooters or bikes at any time and any location that has disrupted the public space severely. So the government only allows docking-based service for scooter sharing. And then we reconstructed the historical trajectory. I'm not going into details for this. And here is the important thing. We find that in downtown area of Singapore, nearly 16%, that is 1584.8% of the trips are made not by the users, but by the employees of the company. And in which nearly 31% of 31.6% of the trips are made for charging these electronic scooters. Oh my God, my dear friend, this is very costly. This is the first impression when I came up this number, and I realized it is because Lean, to Unicom, worldwide Unicom, Lean it pays around $3 to $12 to charge one scooter, and Bird pays around $5 for each. So if we paid at Bird pays $5 for each for two small areas, 4 weeks of time, 28 days, we're gonna spend at least $34,000 US. So what happens for a year? That would be more than $400,000 US. Imagine that this is just a two small area, not whole of the city. So what happens for a whole of the city, like in Los Angeles? That would be more billions of US dollars. I took these two photos while I was in Singapore, in National University of Singapore. You can see that people they do the repositioning or rebalancing, either ride a scooter and hold the other one, or by using logistical vehicles. So my finding is also just proved by a report saying electronic scooter charging is a cut-through business, and Lean wants to fix that. So what can we do? So to solve this problem, we propose our solution. That's what we call it solar charging for shared scooters. I borrowed this picture. I give the citation. And you're going to see that the basic idea is that the scooters are parking at the parking space during the daytime, and they can get charging as long as there's sunshine, right? So we utilize the model as I just introduced. We estimate the solar distribution at a very high temporal and very high spatial resolution. Based on determining the location of a parking space regulated by the government, we can estimate, let's say, the area for each parking space, what's the size of a PV module we need to use to generate enough electricity, which also concentrated by the surrounding buildings, right? So this is the first. The second, I develop a real-time shareability network. So in this network, we consider real-time weather condition. Essentially, it's not the real time, but the historical weather, because In this case, we can have a statistically significance index, right? To get rid of the unstable weather. But for so-called real time, because the temporal resolution is very high, okay, we do the real-time simulation. And also the second, we do the simulation of on-demand, which means the request from the real users and the availability from the shared e-scooters. So scooter get charging when they're parking at the stations, and the electricity, the battery, okay, the electricity of the battery is deducted when they are moving to serve the trips. And also we built an IoT solution, which means that we need users to make a reservation, let's say 5 or 10 minutes ahead of time. So we can utilize these 5 minutes in the server or in the back server side, in the system side, we can do the optimization, dispatching, okay, to maximize the serving rate and at the same time minimize the total trip distance. So in this case, we can have less energy consumption and totally less waiting time from the users. So we do the real simulation. We find that we only need around 24 to 67% of scooters to serve more than 97% of the real trips, when the reservation time is 10 minutes. So for each location, every location in downtown area, we need 1 square meter, 0.25 square meters PV module in US to serve nearly 100% of real trips. In total, the PV size is 39 versus 91. So we haven't calculated the economic cost very in great detail, but we intuitively think that this is very sufficient or efficient compared with the conventional charging solution. If you compare the installation cost, the cost of PV modules itself, even you consider the operational cost, this is significantly smaller than the conventional charging service. Okay. Someone asked, my friend says, hi, yeah, it seems this is a good solution, Felix. But what happens if there's no solar charging because of the continuously cloudy or raining days? Well, to answer this question, I did an extreme test. So I assume that there's no solar charging, there's no sunshine at all. So, but all the scooters in each independent experiment, all the scooters starts from the 4 battery level, 100%, respectively from 150 watt-hour to 900. So this is just a variation of the electricity capacity for each scooter, and we do the same simulation. In this case, we find that we can still support more than 90% of trips for 20 days in downtown area and 3 days in National University of Singapore in US. So what does this mean? So this means that we can achieve nearly a 98% reduction of charging trips. Still, if we pay that the bird pays $5 for each, now we can save more than $1,000 US dollars, 2 small areas, 4 weeks of time only. For situation in Nordic countries, even I stayed in Stockholm before. So I look at this publication. It's in Tordingham. It's in Norway, right? More north part than Stockholm. So the major focus is to look at the distribution of the solar energy throughout the year in different months. So I think it's, in Sweden and in Stockholm, it's also follows the same pattern, which means we have abundant of solar energy, especially during the summertime, right? So we have very significant seasonal variation. This is the first. Second, if you look at this picture I just downloaded, this is global horizontal irradiation. Look at, this is the keyword, horizontal surface. It's not the optimal layout for the PV module, because if we install PV module, for example, even on the rooftops, we should consider different azimuths and insulation angle. So in this case, this for horizontal, daily average for Stockholm is around 2.8 kilowatt hour. So kilowatt hour per square meter. So I didn't calculate in detail mathematically, but I realized that if we install solar panel in a good way, which means a good the optimal atmosphere and orientation, we may probably can achieve nearly 1 kilowatt hour per square meter every day. If in this case, it's already much better than I previously expected. Second, this is the main campus at KTH. We see that there are already some PV modules installed on the rooftop. So when even before this invitation of this webinar, I've already looked at the possibility to build this PV module on some shading boards. I even talked with my colleague in another department here at Hong Kong PolyU. So the significance is that we can generate electricity at the same time. This is one. The second, we can allow less amount of solar energy go indoors, so our indoor environment is getting cooler. This is significant for Hong Kong and Singapore that we use air conditioning extensively throughout the year. So in this case, we can use air conditioners less. And when I wrote the research proposal, I even look at the buildings I studied before here at KTH. You're gonna see these white sunshade boards. It's pretty much the same as the figure I jotted here. So this red dots, red area means the outdoor location, we can install solar panels. In this gray area, which means that in any case, we should not install solar panel, otherwise you're gonna lose money because the shading from the surrounding buildings. So I think this is an interesting way to investigate the possibility of using solar energy in Nordic cities. And consider that during the summer, sometimes in the winter, this elevation angle is not that much large, not here, not like here in Hong Kong, even in Singapore. So I think sometimes these sun shading boards can generate even larger amount of electricity than the rooftop. That's my thinking. Yeah, during the past years, we've already achieved some impacts. Yeah, that's it. Thank you. Thank you very much.